Hi, my name is Koon Seng and I'm from DBS. I'm working from home and I'm delighted to be sharing this SRE conversation sessions with you. For today, I'll be speaking at a topic that might at first glance seem a world apart from the usual type of applications that are associated with SRE. I'm talking about batch computing. Yes, the mode of computing that is typically associated with mainframe and legacy applications. What I hope today is to change your perception about batch. No, I won't be trying to convince you that you should do more batch computing. Rather, I'll be trying to show you that there are many practical and useful lessons that the discipline of SRE can bring to batch operations. I hope to show you that many of these can bring about better ways to optimize, troubleshoot, and manage these applications, which are an integral part of large financial institutions. So let's begin. So why talk about batch? In DBS and many large financial institutions, batch applications are really the workhorses and often the backbone of the bank. In DBS middle office where I work, batch applications are responsible for generating most of the critical daily operational data that the bank runs on, as well as important reports that we need to submit to our regulators worldwide. Our batch job runs on all types of hardware, from mainframes to virtual machines, and over the course of a day, over 200,000 jobs are being run, with over a third of a million state changes being recorded. For many of these jobs, late start, late completion or errors can impact the bank's operations, its financial position, customers, and provoke sanctions or fines from regulators. Aside from this, there's also reputational risk at stake, especially if customers are impacted. So you can see the role and the nature of batch operations in the bank, like DBS, it's a very critical. It is not only the sheer number of jobs that need to be orchestrated and executed every day, there's also this mind-boggling dependencies that jobs have on one another, something that we'll see later on. This makes it humanly impossible in many situations to predict the final outcome if intermediate jobs are late or in error. Batch operation thus is more of an art than science. Through long experience, batch operators often rely on gut feel to make a call when jobs run late. However, as no application is static forever, changes in code or schedule or dependencies can really mess up gut feel. Something that used to run in 5 minutes may now require an hour because of a code change. How will this impact downstream jobs? How can we take into account all this constantly changing information? What can we do to improve this? With the advent of AI and machine learning, a natural question comes to mind. How can we use these techniques to improve the way we operate batch applications? In what areas can we push this envelope, and actually how far can we push this? If you look at SRE practices, several areas come to mind that are potentially interesting, or at least they offer potentially interesting possibilities. These includes the areas of capacity management. Basically, we're asking the question, how can we tie business volumes to resource utilization, such as the number of cores used, memory or I/O, to batch performance? Namely, how fast can the batch complete? Can we use machine learning techniques such as regression to model these relationships and to predict performance or utilization? Architecture. How can we analyze the web of dependencies, which can be time-based, it could be sequence-based or token-based, to derive a critical path? Can we use graph algorithms to simplify paths, detect deadlocks, or revise schedule times to minimize overall completion time or resource utilization? Anomaly detection. How do we know that an application is running normally, given that some degree of lateness or failures are normal and can be tolerated? Can we construct an execution profile of each job based on the behavior of its other dependent jobs? Are there hidden dependencies not captured in the system? Can we detect these through correlation? Error budgets. How can we design enterprise-wide error budgets given that batch applications tend to be tightly coupled to each other? When an application completes late because of a delay in its upstream neighbor, how can we attribute this back to the upstream neighbor's error budget? How should an application be penalized at all if the cause was due to someone upstream? Performance management. This is the area that we will be focusing on today. How can we reliably predict how long a batch will run, given that there are late jobs and failures in between? More on this on the next slide. So why are we interested in predicting batch run timings, and what else can we do with this information? Well, firstly, if we know what time the run will complete, we will know if it's going to be late, which is primarily what we're concerned with. If we know this far enough in advance, we can take preemptive actions. This can be as simple as notifying downstream systems of the delay very early on, or initiating impact assessment and escalation, if necessary, to the appropriate authorities. Or, in some cases, letting the application make do with partial information, or in some very specific cases, filling in missing data with old or previous values. Simply knowing how late the run will likely be often reduces the anxiety of needing to constantly check, a mental battle between uncertainty and hope. In addition, through the process of estimating and modeling a batch run, we can discover which jobs whose behavior have the greatest impact on batch completion timing. Special attention can then be paid to monitoring these jobs or improving them to reduce overall batch execution time. We'd also like to create a statistical baseline of all jobs in a run, what time they usually start, and how long do they usually run. This will allow alerts to be raised when these thresholds are breached. Now you should note that a breach of a single threshold of a single job may not have any impact on the overall run. Nevertheless, your level 1 support team would probably want to receive these alerts anyway, to treat as a possible early warning indicator that something unusual is happening. Finally, because with machine learning, we are essentially looking at past behavior, and as we all know, past behavior may not always be a good predictor of the future. This information could always be used just as a supplementary source to firm up a hunch or a gut feel. Our experienced operators would probably be more reassured if their gut feel got confirmed by a quantitative model. Conversely, if the model disagrees with a solid hunch, then we might want to be more careful. So having said all that, let's take a look at an application where we actually worked on applying this. Let's call the application a ledger application. Now this is a typical medium-sized application that runs on weekdays between 6 p.m. and 8:30 a.m. T+1, which means that starts at 6 p.m. and finishes at 8:30 a.m. the next day. This 8:30 a.m. timing is the cutoff timing that the batch must complete without causing a delay to downstream applications. On average, it runs around 634 daily jobs, but the actual number can fluctuate depending on holidays and other complex business rules. At its maximum, typically around month ends, quarter ends, or year ends, the application can run over 1,300 jobs. The largest job is dependent on 177 other jobs nested to 10 levels deep. And the last job of the batch, or the final job of the batch, is dependent on 129 other jobs nested to 5 levels deep. The chart actually shows the daily execution time in minutes, that is on the y-axis, for each run. The x-axis shows the run number. So in this case, since it's a daily job, each time point or each point you see on the chart represents a day. So as you can see, there are over 400 points in the chart, which represents a period of time of more than a year. As you can see, the blue line is pretty spiky. There are no discernible trend, and the variability is quite high. So basically, this is what we're trying to predict. This variability, or basically to predict the batch timing accurately in face of this volatility, which can kind of vary day to day. This slide shows a simplified view of typical jobs in the application. Each job starts at a specific time denoted by the start of the bar and lasts a duration specified by the length of the bar. The job can be executed successfully, shown in green, or result in an abandon that can be retried again later. This is shown in orange. Or it can fail completely, shown as red. Jobs can be executed only once in a run, or once a day, or they can get executed multiple times in a run, as in a recurring job. The duration of a batch run is the time from the start of the first job to the completion time of the final job. As you can see, jobs can be dependent on one another, meaning that until a dependent job completes, the other job cannot start. For each run, there is a cutoff time in which the last job must complete. Completion after the cutoff time is deemed late or delayed completion. This is a measure that we derive SLAs and error budgets on, and it's something that we strive to meet with every batch run. This slide visualizes the dependencies of the most complex job. It looks like a ball of spaghetti actually, but it's actually a directed graph. The job in question here is the root of this graph, and it's marked by the red ellipse you see on the very left. All the other things to the right of it are jobs that it depends on. Like I mentioned earlier, by dependence we mean that those jobs must complete before our job can run. These other jobs have dependencies on yet other jobs, and hence there are lines and arrows everywhere. Some of these dependencies cross over to other upstream or downstream apps, so it's really not humanly possible to reliably trace these dependencies beyond just a couple of hops. So having seen the complexity and scale of a typical batch application, how can we approach the problem? Specifically, how can we model it? If we think about it, there are really four types of features that we can use to model a batch run. These are the batch duration, meaning how long a job runs. Intuitively, if every job runs longer, the batch itself will run longer. The other feature is the start time of each job. If many jobs start late, it is highly likely that the batch run itself will execute longer. This can happen because of delays from upstream systems. Note that just because a job starts late doesn't mean that the job itself will run late or it will run longer. Thirdly, we can use historical timing, meaning that if a batch runs longer today, there is a chance it will run longer tomorrow. Now this can happen if there were changes in the code that altered the behavior of the application. This behavior is likely to be persistent, meaning that its behavior will continue into the future. Alternatively, it could be the case that Monday batches always run longer than Tuesday batches because it processes data accumulated over the weekend when the banks are closed. In that case, a good predictor of next Monday's run would be last Monday's run and not the day before. In any case, it's basically using the history or historical runs durations to basically predict the future runs. Lastly, we can use a combination of all the above features by building a machine learning model that stacks a model over other models. So this is useful when each model is strong in certain situations but weak in others. A stacked model will learn the best from both and give a better accuracy overall. The diagram on the right just depicts this information. Using the first approach, we constructed an XGBoost model where the features were the duration of each of the jobs in the run. We chose to use XGBoost, although probably any gradient boosting technique will work, as it was a natural choice for performing multivariate regression, and we had good experience using it in the past. We then fitted the model to about 3 months of daily data and analyzed the importance of the features with respect to the predicted value of the batch runs. To do this, we used an approach called Shapely Additive Explanations, which I provided a link to the Python implementation in the slides. This technique provides an optimal way to estimate how the predicted value of a model can be attributed back to the value of its component features. I won't go into the details of how this works because we don't have time, but nevertheless, this technique has been gaining popularity recently because it allows us to build models which are relatively easy to explain. In a nutshell, what it does is it allows us to rank the features, which are job names, by their influence to the duration of the whole entire batch. The diagram on the left depicts this for the top 20 most influential jobs. The length of the bar denotes the influence, and on the left, the y-axis, these are the job names, the truncated job names. The diagram on the right actually plots the influence against job duration, and each point you see in the diagram is actually a execution of a job. The y-axis is the measure of the influence of the job on the overall batch duration. Is basically the same as the length of the blue bar you see here, but obviously I'm plotting a lot more than just the 20 jobs. I'm basically plotting all the jobs. The x-axis is the duration of the job in minutes, how long the job runs. So as you can see, there's actually really no strong correlation between job duration and influence. There's a little bit of slight positive correlation. I draw a line there, but it's really not very convincing, actually. The only exception is there are 3 jobs which are shown circled in red in the chart there, which have actually very high influence, and they're actually relatively long. So if you look at the chart, it's actually longer than 100 minutes. So by and large from the plot, you can see that the execution duration of most jobs, they do not have much impact on the overall batch runs. This means that except for 1 or 2 jobs, right, except for this couple of jobs, right, monitoring the vast majority of the jobs to detect long-running situations, in all likelihood, will not provide a very good accuracy. In this slide, we show the result of taking the second approach, using the start time of each job relative to the start time of the batch run to build a model. Once again, using Shapely Additive Explanations, we can construct a ranking of job influence on batch duration and this is depicted in the diagram on the left. We once again see a few jobs having high influence, but the majority having lesser influence. However, the diagram on the right, which plots the influence against the time it starts, is different. It is actually very promising and interesting. And this is because we can see a relatively large number of jobs circled in red having strong influence, but starting at around 400 minutes or around 7 hours from the start of the batch. This is roughly around midway through a typical daily batch run. What the data is trying to tell us is that roughly halfway through the run, we should theoretically be able to start making accurate predictions. In other words, we should potentially be able to reliably predict around 7 to 8 hours ahead of time. This added buffer would allow time to notify downstream applications or other contingency plans or actions to kick in. Encouraged by this last approach, we analyze the historical data and simulate how prediction accuracy will improve over the course of a batch run. We basically did some backtesting with the data, and the results are shown for the two approaches in the diagrams above. The left diagram depicts the job duration model, while the right one, the job start time model. The y-axis of both plots represent the mean absolute error in minutes, while the x-axis charts time from the start of the batch. The blue line shows the error dropping or the accuracy increasing as the batch progresses. As expected, around the 7 to 8 hour mark, the error figures start dropping off steeply for both models. However, for the model on the right, the drop is much more faster and the gradient of the curve is much more steeper over all time points. This leads us to choose the second model as the primary basis for our work. In addition to this model, we also incorporated a few refinements. One of the most important was to include historical batch run timings on a day of the week basis as an additional feature to the model. This means that we add an additional number to the model, which basically takes a look at the last, whatever day of the week, the last batch run timing of that day of the week from the previous week. This significantly improved the overall accuracy of the model. And we have other refinements which I'll show next. So one of the most significant improvements came from this concept of model simplification. Basically, as the daily batch progressed and more jobs completed, right, more and more features get added to the model. So from the previous plots and the slides I presented, right, we wondered if all this actual additional data was making the model more accurate or simply adding more noise to it. This was because, as we saw earlier, many of the jobs had little influence on the overall batch runs. And so we did an experiment and basically pruned the model at each prediction time point by constructing a simplified model from the original model using the top 10 features only. And the result, surprisingly or perhaps not surprisingly, were actually more accurate. So the two histograms above, the arrow histograms, basically showed the results. The bottom histogram was built from the model with only 11 features, while the top one had 313 features, and you can visually see that the histogram below is narrower, and has a higher peak than the other one. So literally, as the saying goes, right, more is not always better. This slide shows how the actual predictive dashboard looks like. Right in the middle, there is a clock that is basically showing the last time point with data, and this clock will advance as time progresses in 5 minutes intervals. On the left, we see a progress bar showing the progress of the batch run completion in percentage terms. And then below the clock, you basically get an estimate of the completion time range. Basically, with the upper and lower bound based on a certain percentage of confidence that we have. On the right, you actually see a error histogram of the prediction based on the same features jobs that you have right now historically over time. So this gives a way to gauge the confidence of the prediction. If you see very narrow error bars, you know that your predictions are pretty accurate. If you see very wide, then likely the prediction might not be so accurate. Below, you get the actual numbers in terms of mean absolute error, and mean absolute percentage errors, and root mean square errors, so on and so forth. And then finally, below here, you see a trace of the jobs which are executing or which have actually completed execution. And they are color-coded. You see them in the Gantt chart laid out over time. Here we see the accuracy of the system over a 2-week period. The red line shows the mean predicted end time of a run, and the orange line shows the actual completed time. So each time point on your x-axis you see different dates. For each day, the prediction was made around midnight, which is around 8.5 hours ahead of the target cutoff time, which is shown by the dotted black line there. So as you can see, the predictions are pretty accurate. The mean error rate so far is around 17 minutes. Historically, with the initial data set of 3 months, now that we've been running for some time, the actual error was actually lower than that, to around 10 minutes or below. So on some days, it's actually accurate to the minute actually. In summary, we started with the motivation of why we looked at applying SRE principles to batch operations. We gave a brief outline of the possible approaches and how we used them to develop working models. We saw how we could realize these models as well as refine them in a practical manner, and showed how we can operationalize the system and how we might be able to use these predictions to build an AI-based dashboard. Finally, we showed some figures on the accuracy of the approach for the ledger applications. So I'd like to take some time to circle back to my original point of the role of SRE in all this work. Firstly, from the point of view of observability, the project gave us a good reason to build a 5-minute data feed from our batch system. Previously, the usage of the system was primarily based on alert and event-driven, and required rules such as thresholds to be set up to trigger events from specific jobs. On early warning, the approach shifted some of the work our folks did from being reactive to predictive. This also reduced the possibility of someone overlooking to do something manually or check something manually, because all the batch statuses are checked by the machine now automatically. In terms of being data-driven, the approach eliminated selective bias that frequently occurs when human judgment is involved and replaced it with quantitative data-driven models. This is arguably one of the biggest differences. On the automation front, once configured with the appropriate data feed and job names for the start and end jobs, the system does away with human intervention entirely. And although the predictions are automatically generated, we still see a need for human oversight. This is because for any model to be accurate, we usually discard outliers in the process. This means that predictions generated are accurate only when the system is operating within certain bounds of normality. In the case of major outlier events, right, the model should not be trusted. And basically, this comes down to the principle where, supervised machine learning models are typically very good at interpolation, but extrapolation might be a bit risky. Finally, each model can be hosted independently from the pipeline that carries the data. Essentially, the models subscribe to only the data for the app for which they are doing the prediction. Since the final refined models use only a fixed number of features, typically like top 10 features, the models are somewhat fixed in size. So this allows easy horizontal scalability by simply adding hosts for each new application in most cases. Thank you for your time, and I certainly hope to see you again in the next future SRE conversations. Thank you.